So there is two kinds of approach from accessing leaf area. Either there is reconstructing approach, so typically triangle, where you will try to fit and reconstruct surface, but it requires often a lot of points, and if you have really thin material, as in Mediterranean context, it will be hard to work. That's why we choose statistical approach. We try to relate the amount of intercepted points in a volume to the amount of vegetation. So it's particularly adapt when you have needles and where you have really small leaves. So first, we developed a numerical simulation framework to try to estimate the leaf area. In fact, leaf area can be accessed to the coefficient of attenuation, which is really the density of matter in your volume. So basically, it is quite different. So we use voxel, but it's not like empty or full voxel. It is voxels that are much bigger, several centimeters, and within each voxel, we try to estimate the surface of leaf area. So you can do that by inverting the Beer-Lambert law, so accessing the transmittance. So then transmittance you can estimate it with the ratio of beams that went through the voxel or that were intercepted inside the voxel, and then inverting transmittance and found the coefficient of attenuation. And there is another approach, which is the contact frequency approach, where you relate on the distance traveled by your beam inside the voxel. So it's a more richer approach because you have the full distance travel and it's used the full potential of the TLS, which is the 3D instrument. So we compare this approach and we derived two estimators, and we tested a lot of the sensitivity of this estimator to the size of vegetation element when the number of beam is low, for example. So here is the final formulation, and we corrected bias for this. For example, when the number of beam is low, here are the normalized expectation. So in blue, it is the contact frequency estimator uncorrected, as available in the literature. So it's Martin Bellan estimator, which is really biased when the number of beam goes close to 10. And also, when a lot of beams are available, the size of vegetation element can easily yield 5% bias. So we corrected this bias, and you can see that you can have a very unbiased estimator based on constant frequency, and we also derived confidence interval. So this is purely theoretical, and we validate that on the field. First, at branch scale, so we do that in indoor measurement with two riggers, furrow, and with two LiDAR, the furrow and the rigger. And we scan branches at several distances from 2.5 meters to 20 meters in various conditions, fully foliated to completely defoliated, on three species, Mediterranean species, Quercus pubescens, Quercus silex, and Pinus halepensis. So with 10 centimeter voxel, we had quite good result because we have, what I forgot to say is that there was destructive reference of those branches, of course, to evaluate our estimator. So with the 10 centimeter voxel, there was quite good result, almost unbiased. But when you use, for example, 50 centimeter voxel, you introduce a clumping effect with large underestimation. So fortunately, those effects can be calibrated with the voxel size, and you can really correct for that for all LiDAR we tested and all species. And for the furrow instrument, we also found that when the distance to the target increases, there is a large overestimation effect that can be also corrected. So once you integrate this correction, whatever the species and whatever the used instrument, we succeed in having 20% mean absolute error in our branches. Then we validate at 3 scale because, of course, for branches it was working, but with higher leaf area density value, with a lot more distance occlusion, there is no guarantee, so we try it. And we destructively sampled 15 trees to have references by vertical layer. So here is the total leaf area predicted versus references. So in most cases, we have less than 25% error, but for some trees, so the largest, big error can be observed. For example, this one, which is predicted less than twice the total leaf area. Also, the vertical profile is well captured. So you can see here the black crosses of the references. And there is some voxel size that are more adapted given the species. So here is a deciduous, Quercus ilex, which works well at 10 centimeter voxel size. And here is a Quercus pubescens, which works well at 50 centimeter. Of course, there was some occlusion in the tree, as the previous presenter said. So we built a virtual scene to assess this effect with a spatial correlation of the vegetation. And what happened is that obviously occlusion mostly occur in dense density area, and then those occlusions spread in the upper layer. So you have really a large underestimation, because what is usually done with occludal voxel is ignore them simply, but those voxels are the one with often the most densest leaf area. So it suffers from large underestimation. Using larger voxel prevents such underestimation, but of course you have clumping effect you have to correct, but still it is a better option than suffer from occlusion, because occlusion is really difficult to correct because you have, by definition, no information. Still, we developed a tool to try to deal with occluded area in voxel approach. Our estimator, as I said previously, has a variance and confidence interval, and we try to adapt kriging approach to occluded area. So basically, stand of course, the tree are really have a spatially corrected structure, and we tried to use the structures to build the variogram and make interpolation. Like, for example, when you're in a crown, there is a high probability that the occluded voxel beside the one you see in the crowd also have vegetation, on the contrary to empty area. So we adapted kriging in the senses, and we also adapted interpolation between voxels with a confidence white, meaning that voxels that are well explored count more than voxels with few beams. So this yields quite good results. So first on the simulation scene, so here is the probability density of error, and in blue you can see that when using this method, there is a drop of error measure, which is significant, and that's what confirmed on the field with really reducing error in unexplored voxel. And the advantage of this method is that it can also correct the poorly explored voxels, meaning that neighboring voxel gonna help to do the estimation of the one with few beam. So all is published. So thank you for your attention, and these tools are freely available. For example, in the AmapVox software, where we can provide estimation of leaf area density, and I hope we can collaborate to diffuse and improve this tool. Thank you for your attention.
Thank you very much. Very interesting. Any questions? Please, Marcus. Could you please wait for the microphone?
As far as I have understood, you have used always only one scan, right?
Sorry, can you repeat?
you have used only one data from one scan position.
Depend.
Because then my question would be, if you use data from several scan positions in the upper canopy, if you have really a slight wind, you double the leaves in the point cloud. How you deal with this?
If I use several scan positions?
If you have a merged point cloud?
Yes, there is several point cloud. There was 5 scan for 20 by 20 meters, 10 by 10, and there was 5 scan, and so it is a single echo. It's Faro type simulation, but still there was occlusion even with the 5 scan. Here you can see in green it's the references, and even here in violet it's the 5 scan design, and still you can have occlusion. And in Mediterranean area, we even scanning an isolated tree with 5 position.
I was not speaking about occlusions, but the leaves, if they move between the scan positions.
Okay.
And
so
this happens always.
Okay, so we scan with no windy condition, like really in the morning when.
Then you were very lucky.
It was complicated, but it was early in the morning with no wind.
So, please, a very, very short question.
You've shown that you have different information from the different voxel sizes. This hints to the point that a multi-resolution or multi-scale approach could be a solution, because the different resolutions contain different information, and how the information is changing over the resolutions could maybe help.
Yes, it's true. And but for example, for an isolated branch, you consider the same volume and the same vegetation, and even in that case, summing the 10 small voxel compared to the 50 centimeter one, you have almost twice underestimation. So there is it's due to the convexity when you inverse the transmittance, and there is really a clumping effect.
Thank you very much.